Coffee plays an essential role in people's lives around the world, and some may consider it just as important as drinking water. What's not to love? It tastes good and keeps you awake. What makes us feel this way is actually a molecule called caffeine. It stimulates your central nervous system, making you feel more alert and energetic. However, too much of it can make you feel jittery and cause headaches. In this experiment, I explored different ways to extract caffeine from coffee grounds. I wanted to see which method results in the highest concentration. After extraction, caffeine can be used for headache and migraine medications, dietary supplements, and energy drinks. This process is also used to make decaffeinated coffee. The variables I tested were the flow rate of water and coffee grind size. In one set of experiments, I poured water over medium coffee grounds at a slow, medium, and fast flow rate. In another set, I poured water at a medium flow rate over fine, medium, and coarse coffee grounds. I did this to see how the flow rate and coffee grind size affect caffeine extraction. I predicted that at lower flow rates, more caffeine will be extracted. This is because the water can spend more time with the coffee dissolving it. Also, I noticed that when I let my tea or coffee sit out for a while, the taste is much stronger, meaning that there are more flavor molecules. I thought caffeine might follow a similar trend. I also predicted that finer or smaller coffee grounds would extract more caffeine since they have more surface area. Let's say that a coffee ground is the same shape as a cube, which has 6 surfaces. But if we split that cube up into 20 cubes, we get 120 surfaces. This means that there are a lot more places for water to touch and react with. I followed the same procedure for both the flow rate and grind size experiments. First, I made a calibration curve. A calibration curve translates what the spectrophotometer tells us. For example, say you have a sample of caffeine you just extracted. You put it into a spectrophotometer, which is a machine that measures light. The spectrophotometer tells you that your sample absorbs 0.7 angstroms, but that means nothing to you. You want to know the caffeine concentration in your sample, so you go to your calibration curve to find the concentration like so. The next step is solid liquid extraction, and is just like how you make coffee. Hot water is poured over some coffee grounds in a coffee filter. The hot water dissolves the coffee grounds, allowing the caffeine and flavor molecules to pass through the filter. What you're left with is a nice hot cup of coffee. In my experiment, I used a glass column packed with cotton, which acted like a coffee filter. Coffee samples were then taken about every 40 seconds. The last step is separating the caffeine from coffee through liquid-liquid extraction. This is done by adding dichloromethane or DCM to the coffee. Caffeine dissolves better in DCM than in the water in coffee. As a result, the caffeine leaves the coffee and into the DCM. The coffee mixture is then shaken to create these layers. It is similar to how oil and water act when mixed together. Because DCM is denser than water, it will be in the lower layer where it can be removed easily. The sample is then put in a spectrophotometer as mentioned before in step 1. This is a graph showing caffeine concentration versus time for slow, medium, and fast flow rates. The red triangles are always above the other ones, which means that the most caffeine is extracted at a slow flow rate. Similarly, because the blue triangles are above the navy circles and light blue squares, the most caffeine is extracted at a medium grind size. These results are especially important for pour-over coffee drinkers, as my experiment most closely resembles this brewing method. If you want to get the most caffeine out of your beans, pour hot water over your grounds slowly or let it brew for longer. Also, be sure not to grind your beans too much since finer grounds can prevent water from flowing through the filter and thus prevent caffeine from going through. However, there are many other variables that affect caffeine extraction, so try it out yourself.